Now let me talk about matrix multiplication. Matrix multiplication involves a bit more work. So let me first start with vector multiplication. So what is a vector? A vector is just a single row, a single column matrix. So here we have a row vector 1 by C. That means this matrix just has one row and C columns. So here, let's say C is 4, okay? So X is equal to X1, X2, X3, and X4. Now we have a column vector, okay? We have a column vector, beta, let's say R by 1. And that means we have R rows and one column, okay? So X is a single row matrix, and the beta here is a single column matrix, and beta 1, beta 2, and beta 3. How about multiplying X by beta? So here, X is called multiplicand matrix, and beta is multiplier matrix. And what we're going to do is we're going to use X element-wise multiplies beta element-wise, okay? What that means is, okay, we're going to use the first element in X to multiply first element in beta, okay? And then for the second element in X, multiply by the second element in beta, so on and so forth. And what we're going to do next is to add them together. So X1 multiplied by beta 1, X2 multiplied by beta 2, X3 multiplied by beta 3, and X4 multiplied by beta 4. Now here shows that the number of elements, okay, in the X vector, that is a row vector, has to be equivalent of the number of rows, okay, in beta. Okay, let me repeat. The number of columns, that is the number of elements in a row vector X, has to be equal to the number of elements in beta, or number of rows in beta. And otherwise, it is what is called non-conformable operation, okay? So the number of columns here in the first matrix, that is this multiplicand, has to be equal to the number of rows, okay? Number of rows in the multiply of the second matrix. So X is what? Here is 1 by what? 4. That is the dimension of X. What about dimension of beta? Is 4 by 1. Now, once we carry out this element-wise multiplication, what we're going to do is we add them together. So summation. So the summation becomes beta 1, X1, beta 2, X2, beta 3, X3, beta 4, X4. Then sum across. Summation. Okay. So that is vector multiplication. That is vector multiplication. Okay. Let's move on. Matrix multiplication. Now, matrix multiplication is when we have two matrices, right? Each having multiple rows and multiple columns. Right? Okay. So how does matrix multiplication, the full-blown matrix multiplication, work out? So let's say we have two matrices, A and B, right? So for matrix A, we have R rows and K columns. For matrix B, we have K rows and what? C columns. Notice that the number of columns in the first matrix, that is the multiplicand matrix, the matrix that is to be multiplied, and the second matrix, okay, Here I'm talking about the number of rows in the second matrix, okay? Has to be equal to what? The number of columns in the first matrix multiplicand. Okay? The number of columns of the multiplicand matrix has to be equal to what? The number of rows in the multiply matrix. Then we're going to have conformable multiplication. Otherwise, it won't work. Then the matrix product C, okay, which is going to have dimension R by C, that is R rows and C columns, okay, is equal to here okay, each element in that matrix is going to be equal to, well, also the multiplication of what? Rth row from A and the Cth column from B. Cth column from B. So here I use lowercase to denote that. Okay, and summation sign. Okay, so know that element C RC is the vector multiplication of row R from A and column C from B. So we kind of decompose the full-blown matrix multiplication into a vector multiplication. So here we have an example. You will know much better what's going on here. Right, so we have two matrices. The first matrix is composed of 1, 2, 3, 4, 5, 6, right? And the second matrix comprises A, B, C, D, F, G, tri. You know, just some unknown numbers, right? Denoted by English letters. So what we're going to do is for the first row and first column element of the product is equal to the summation of the multiplication of the first row of the first matrix of the multiplication matrix and the first column of the multiply matrix. So we use 1 multiplied by A, 2 multiplied by D, 3 multiplied by G, and sum across. What about the second element? Well, the second element is in row 1 and column 2. Okay, that means it is a product of the first what? Row of the first matrix and what? The second column of the second matrix, the multiply matrix. So 1 multiplied by B, 2 multiplied by E, 3 multiplied by H, then sum across. Let's pick another element, random element. Let's say row 2 and column 2. So row 2 and column 2, it is the product of the second row of the first matrix of the multiplicand. Multiply element wise and then summation, okay, with what? The second column of the second matrix, that is multiply matrix. So the second row of the first matrix, the multiplication matrix, and the second column of the multiply matrix, right? 4 multiplied by B, 5 multiplied by E, and 6 multiplied by H, then sum across. Last example. How about the second row and third column? Well, for the second row and third column element of the product matrix, it has to be a result of multiplying what? The second row of the first matrix, this one, the multiplicand matrix. And then multiply that by the third column of the multiply matrix, right? 4 multiplied by 3, 5 multiplied by F, 6 multiplied by I, and sum across. Okay. it's a little bit more, computationally expensive, but still pretty straightforward because this is simply a combination of multiplication and addition. Then adding to that, we have what element-wise operation, right? So here we have a matrix multiplication example for regression analysis. Okay, so here we have what observations, a column of observations for the response variables, right? Values for the response variable y1 to yn. Then we have an X matrix, right? Denoted by their row number or column number, right? Multiplied by beta. Then disturbance term. So here is this, we have this matrix expression pretty straightforward, right? Y equal to X beta plus epsilon. But how to spell that out using concrete terms in a matrix? We have the second part. Well, to perform multiplication, let's say for X beta. So we have first row from X and this column from beta. So how to perform the multiplication, right? Well, we pick the first row from X, then a single column beta. We do element-wise multiplication, sum across. So 1 multiplied by beta 0, that is interceptor, right? Beta 0. And beta 1 multiplied by x1, 1, we get this term. Beta 2, x1, 2. Until we hit the last element, right? Beta k, x1k. Right? So that is what? That is the 1 element of the product, right? And we can go pick the second column, a second row of the X matrix that is multiplicand. Multiply that by the column vector of beta. What we get again? We get beta 0 plus what? Plus beta 1. Well, for X is second row, first element, right? Plus what? Beta 2. Well, for the second X is what? X second row, second column. And we continue until we hit what? Beta k, X what? 2k plus epsilon 2. And then we go on until we hit the last element, right? The nth row and still first column, okay? So the last row of X multiply, that vector multiplied by this column vector. So beta 0 multiplied by 1 is beta 0, and beta 1, X n1, right? Nth row, first X covariate. Beta 2, X n2, until we hit what? Beta k, X n k plus epsilon n. Right? So here we see how matrix multiplication can help us simplify the notation. So from here, right, directly we can get to here, and they're equivalent. So we don't have to lay out such complex and tedious, scalar operations in matrix format, right?